So this is the second part of chapter 24 on nuclear chemistry, and we're going to start out just kind of finishing up some loose ends from last time. We talked a little bit about fission reactors. I just want to make sure that you understand that's the type of reaction that we do in our nuclear power plants all around the country, and we saw a video in class where you got to understand a little bit more about it. It produces hazardous waste, and some of the waste, you know, there are differing feelings about this, but there are ways to estimate it that there are about 10,000 years or more that some of this material is hazardous. Actually quite a bit longer than that, but there's a point where they consider the hazard to be minimal. So you got to think about that. Right now they're burying it in a place in Arizona, and you know that's the plan now. Maybe some other better solutions that maybe one of you guys will think of. Within the reactor, several different things that we could address, and we're not going to spend a whole lot of time talking about the process, but there are fission reactors called breeder reactors that produce more fuel than they use, which means that they can pretty much sustain themselves. The standard fission reactor will split something like plutonium, and it will split that into two smaller atoms, and that energy, tremendous amount of energy released based upon E equals mc squared, where c is the speed of light, 3 times 10 to the 8th. So we're starting to think about, okay, let's say 1 kilogram times 9 times 10 to the 16th, tremendous amount of energy that's released from just 1 kilogram of fissionable material. And you know, within the process, a couple other things going on that because they want to be able to control this, we have a process called neutron moderation, and that reduces the speed of the neutrons so that they can be captured by neutron absorption. Of course, we have the rods that are lifted out, and they're able to start doing chain reaction. Then we drop those back into their protective sheath, and that slows the reaction. So it's kind of like a gas pedal and a brake. And mostly computer controlled, but you know, the people run the computers, and they also have that power to make this manually controlled. So we're going to talk about half-life and decay. We've already talked about decay a little bit. Obviously, if something decays, then it slowly disappears. So some of it goes away. And this is what half-life deals with. Half-life would be the amount of time it takes for 1/2 of a radioisotope to degrade into some other element that's more stable. Each half-life, we lose about 1/2 of what we had, and it slows down. Obviously, if you have less material, then there's going to be less collisions of particles, and there will be a slower process. So that's why, you know, let's say we start with 10 grams, and let's just say polonium-218 that has a half-life of 3 minutes. After 3 minutes, if we had 10 grams, now we have 5 grams. Well, the next 3 minutes, we only lose 2.5 grams because half of a half of a half, because there's less material, less collisions, nuclear particles, and so the process continually slows down. And that's basically how you figure these, is just think of half of a half of a half. Every half-life, it decreases 1 more half. So if we had 10 grams, after 1 half-life, there'd be 5 left. After 2, there'd be 2.5. After 3, there'd be 1.25. After 4, there'd be 0.625. So the math of this and the logic is that you can basically just multiply by 1/2 the number of half-lives, and you figure out how much you have left. And there are some other ways to do this. There's a mathematical formula I'll give you if you want to use that. If we're using the logic method here, the first step you want to do is use the material, the information you've got, to find how many half-lives. Okay? There are 2 basic types of problems. One gives you 2 gram amounts. If you have 10 grams and 0.5 grams, then it says how long does it take to do that decay? Well, 10 to 5 is 1 half-life. 5 to 2.5 is 2. 2.5 to 1.25, and then we've got 1.25 to 0.625. Let's say that we started at 10 and it said 0.625 in the problem. Then we just count how many times it had to cut in half to get there. That tells you how many half-lives. So the first thing you do, try to find half-lives. 10 to 5, 1. 5 to 2.5, 2. 2.5 to 1.25, that's 3. And 1.25 to 0.625, that's 4. So you would say 4 half-lives. Then you go look at your reference information and find out, for instance, polonium-218, 4 half-lives would be 4 times 3 minutes. And that would be 12 minutes total is how long it would take. That's the logical way you can deal with it. And you could show your work just by just making a little jumps to show each time it cuts in half. And count them. The other way is you might have a problem that has one mass amount and a time. Well, so the first thing you need to do is find half-lives. Use the time, do dimensional analysis with your possibly useful page that tells you the half-lives. Figure out how many half-lives. So let's say that we'll do that same problem but kind of in reverse. Let's say that you had 10 grams of polonium-218 and you knew that it was there for 12 minutes. Well, how much is left? Well, you could do 12 minutes times 1 half-life over 3 tells you 4 half-lives. So you do the dimensional analysis. Now you know 4 half-lives. Well, then you say 10 to 5 grams, that's 1 half-life. 5 to 2.5, that's 2. 2.5 to 1.25, that's 3. 1.25, 0.625. So you have 0.625 left at the end. That would be the logical way to deal with these. Now I have a sheet that has some practice problems. I've got the first 10 or so worked out on a key that you can check. It'd be a good idea to go through and make sure you could do both of those types of problems. And those are the types that I'll show you on the quiz or the test, so make sure you know how to do those. Now, there is a formula, and I would like for you to know how to use the formula, because what if you don't have something that's exactly like 4 half-lives? What if it's 4.5? Well, this formula will tell you how much you have left, and it doesn't matter how many half-lives. If it's 4.22235, you just plug it in. And the formula is amount final, or amount left, equals the amount original times 1/2 in parentheses raised to the t over h power, and t is time, h is half-life. So here's how we would plug this in. If we had a question like we just had, let's say that we had the one that we dealt with polonium-218. So let's say we had 10 grams, and that would be 10 grams times 1/2 raised to the t over h power. Here's how we enter that on the calculators that I have in my room. They have a y to the x key. So you would enter the 0.5, which is 1/2, parentheses, time, how long has it sat, and that was 12 minutes, over h, which is what's the half-life for polonium-218, it's 3.0 minutes, close parentheses, equal times 10. And that tells you that if you do all that, you're going to get 0.625 for an answer. Very similar to the logic method that we use. And so there you go. Now, you could use this formula if you're that math geek that can say, well, I want to simplify for time or for h or for AO. Any of those things, as long as you have all the information but one unknown, you can solve. And it takes a little bit more work with that. You have to go through natural logs, but I've given you the ability to solve all the types of problems that you're going to see on the quiz and the test. So there's a formula. Here's a practice problem they give you, and you can look at that and make sure you know how to do that. So just kind of some final shots across the bow here. Induced transmutation would be a caused transmutation, either by particle accelerator or atom smasher, or whatever you want to call it. and we can convert one thing into another, one element into another. And there's particles that fly loose, and we study those so that we learn new particles.
Pardon this interruption. I'd like to take a moment to congratulate the following NHS members for their election.